Hi, this is my Math 7502 assignment where I decided to do gradient descent. And the question that we're trying to answer is, how does the basic gradient descent algorithm work? What are some scenarios where it performs badly? And what modifications exist and how do they work? So this notebook demonstrates the inner workings of gradient descent and a lot of its variants. We do explore gradient descent in a convex function and a non-convex function, as well as variants like full batch gradient descent, stochastic gradient descent, and momentum-based gradient descent. So let's run all the code. We first import the libraries, and this is what we define what gradient descent is. So gradient descent is an iterative optimization algorithm used to minimize a differentiable function by updating its parameters vectors with the opposite direction of this gradient, which points towards its deepest increase of the function. And the update rule is ultimately defined by this, where this n-shaped symbol is a learning rate, which is a hyperparameter that controls the step size, and a high learning rate essentially enables high rapid movement but risks overshooting the minimum, while low rate ensures precision but may slow convergence. So let's look at the code. So this stores the weight, stores the function, and this essentially iterates through each step and updates its parameters with the formula. And before we get into some demonstrations, we define some helper methods. So these are some visualization tools I use. Plot path contours shows contour lines where each contour represents points of equal function value. And yeah, so now we apply gradient descent in a convex quadratic function. And what's really important is of form this, which forms a smooth bowl-shaped surface because A is a symmetric positive definite matrix. There's only one global minimum. So looking at the code, we define all the variables, initialize some parameters, and what's really important is what learning rate I chose, which is 0.05, 0.4, and 0.6, which all start at 2.5 and 1.0 with 40 steps. And we then plot it. So let's see the results. And the contours plot shows how gradient descent behaves at different learning rates. You can see the colored paths represent how parameters move toward a minimum with a small learning rate like 0.05. The algorithm moves quite steadily but slowly towards the minimum, and a moderate rate like 0.4 reaches the minimum quickly but remains quite stable, but you can definitely see it's a lot faster. And a large learning rate like 0.6 completely overshoots and diverges, and this is really highlighted in the loss plots. So you can see that the learning rates of 0.05 and 0.4 converge quite smoothly, but you do see that 0.4 does it a lot faster. And then you can see learning rate of 0.6, which completely goes out of bounds. And this goes to our next session where gradient descent doesn't perform as well, which is in a non-convex service. And the function I chose is the Himmelblau function, which has the function this, and 4 global minima at approximately those coordinates. So let's look at the code. So this defines the Himmelblau function. This has the starting points, and here we plot the contours. So each has a learning rate of 0.01 but different initialization points. So this ultimately highlights one of the main challenges of gradient descent, which is in a non-convex function, where gradient descent can easily get trapped in a local minima or a flat region instead of finding the optimal global minima. So in these non-convex problems, you do see that it contains many valleys and peaks, and since gradient descent can only follow the local slope, it only moves downhill towards the nearest minimum, and it has no real mechanism to try and escape that minimum. So this makes the final solution highly dependent on initialization, as shown by how each color trajectory converges to a different path. And this ultimately calls for the need of another variant or modifications to gradient descent, which flows quite nicely to our next section, where we try gradient descent and its variants to a linear regression problem. And the goal is to ultimately estimate the slope W and intercept B that best fits noisy data generated by this. And the optimization objective is to minimize the mean squared error of formula that. And the variance that we decide to do is full batch gradient descent, which uses all the data each update, which is quite stable but slow. Stochastic gradient update, which updates each using random subsets, and momentum gradient descent, which adds a velocity term that smooths, updates, and accelerates convergence. So let's look at the code here. We first define the helper methods used to display this. So here's our full batch gradient ascent, my stochastic gradient ascent, and my momentum gradient ascent. And here we just run all the code, and here is the plot. So we definitely see that full batch gradient ascent moves quite steadily towards the global minima, and it's quite smooth because it uses the entire data set for each data set. And you do see it's relatively slower comparatively to the other ones, like stochastic gradient ascent, which follows a slightly noisier path towards the minimum due to the randomness of using mini batches. And while converted to a similar region, its trajectory wiggles more because the stochastic fluctuations in the gradient section. And then lastly, mentioned stochastic gradient ascent, which is purple, which initially overshoots but then curves smoothly towards the minimum, which really shows the impact of the added velocity term, which helps it gain speed in a consistent direction. Now here is our plot that shows the same thing. So we definitely see full batch gradient ascent decreasing very smoothly and steadily. And you can see that each update is based on the full data set, leading to stable and consistent reduction in loss. And stochastic gradient descent, which is orange, you do see small fluctuations due to the use of various subsets. However, it does make the convergence faster. And then momentum stochastic gradient descent, which starts with large oscillation because of the converged velocity, can cause overshooting early. But we definitely see that over time, the velocity term helps it maintain a smoother, faster progress along consistent gradient directions, where you see that they all converge. And here is our final goal, and we see that it works. So this is for full batch gradient descent, and the blue points represent the noisy data samples generated by our true relationship, which is this, and the orange line, which is the fitted model, which has a form y equals 1.69x minus 0.84. And ultimately, there's a close match between the true and the coefficients indicated that gradient descent successfully minimizes the mean squared error between predicted and actual values, and ultimately showcases how the algorithm works. And that goes to my end.